Number 76, the ion HTE- is an amphiprotic species. It can act as either an acid or a base. And then we have letter C. Demonstrate whether or not the second ionization of HETE can be neglected in the calculation of HETE- in a 0.10 molar solution of HETE. Do I keep seeing HETE? Sorry about that. I meant H2TE, but you get the idea here. I might say HETE. I have no idea why I'm saying that, but we just got to keep going on. Okay. So, in this case, we just have, it's like a demonstration purposes. We just need to see whether the second ionization of H2TE can be neglected in the calculation. Now, we got to get all the way down to the second ionization, which means that we have to do the first ionization, right? Ionization just means that we are losing that H+, right? This is basically acting as an acid, right? I see H is in the front. H is in the front always means that we have an acid, right? So if we're starting with H2TE, the first ionization would drop one hydrogen. You can only drop one hydrogen at a time. So the first ionization, and maybe I'll just say this is first, I got to get from H2TE to HTE-. And then I can get to the second ionization of dropping the final hydrogen. And that would just be Te2-. So, in order to get to the second one, I got to first do the whole shebang for the first ionization, in which H2TE is acting as an acid. So, we're talking about acids. We've got to write a balanced equation, right? So here we go. I guess I'll draw it over here. H2TE. Now with acids, remember, it's just easier to just say, okay, we don't care that it's plus H2O, right? We could just say, okay, this ionizes, and it's at equilibrium because it's a weak acid. H2TE is not one of my 6 strong acids. One of the hydrogen is going to be dropped, so that's going to be H+. And then you just write the remaining. And just like we said here, we had HTE. Okay. Now, anything that has a charge is always aqueous. So this is AQ, this is AQ. And any weak acid or weak base is always AQ. So all of these are going in our Ka expression when we get there. Now, they did say that we started off with 0.10 molar solution of H2TE. So this number right here, that's a initial concentration. They are not taking into account that I dissociated into any hydronium ions or HTE- ions. So I got to do an ice chart. So let's just split it up. Okay, let's write the ICE. We've done tons of these by now in this chapter, right? ICE. Whoop, there we go. I stands for initial. And just like we said, that was the 0.1, and that goes to H2TE. So I have 0.10 initially for H2TE. They did not state anywhere in here that I started off with any H+ ions or HTE- ions, so 0 and 0. C stands for change in concentration, but if you start with nothing, you can only go up from there. So the product side is going to increase, and the reactant side is going to decrease. So this change on the product side has to be plus, and on the reactants it's minus. We don't know by how much, though, so we use a variable. We could literally use any letter, but we always use x. So minus x, and plus x. Keep in mind that these come from your coefficients, but for acids and bases, it's always a 1-to-1-to-1, so that's why you just put x's across the board. E stands for equilibrium. That's when you pull together your initial and your change. So 0.10 minus x is literally, 0.10 minus x. 0 plus x, I could just say that that's x. 0 plus x, I can just say that that's x. All of these, your equilibrium line, is going to go into your Ka expression. Now, I wrote down here 2 Ka values. Which one are we going to use? Well, Ka1, the 1, is the first ionization energy. So this Ka, if I can, this goes with this one. And if we want to bring the other one, where do you think this one's going? Yeah, I'm going to have to use this one for the second ionization. So that's where these are coming from, basically. So I can erase this. Okay, so now since we're dealing with the first ionization, we have to use that Ka value. Let's write the formula, right? Ka always equals just concentration of products divided by reactants. There's two products here, so they're being multiplied by each other, divided by the reactants. If I just wanted to show what's going on here, it would be H plus times HTE minus. Maybe I'll pull that in a little bit. Beautiful. All divided by H2TE. Okay. So let's actually do the math. So the Ka value would be 2.3 times 10 to the negative third equals something divided by something, right? We got the two numbers up top here. We got the one number down here. We have x times x. Remember, it's all equilibrium. And now there's a problem here. If we put 0.10 minus x on the bottom, this is going to turn into a quadratic equation. Now we try to get rid of that as much as we can. We only want to do the quadratic equation if we have to. That's what it's being talked about, if we can neglect it. But we're not there yet because we're not doing the second ionization energy. But what this is basically saying is that this Ka value, 2.3 times 10 to the negative third, this isn't really so low. We've seen Ka values that's like 10 to the negative 10, 10 to the negative 11th, right? This one is relatively, a little bit low, right? But low Ka values means that at equilibrium, you will have mostly reactants, not too much products. So the idea here is that if you started all with reactants and you end with mostly reactants, is this change a really big change, or is it just a little drop? If there's not much change, it's going to be a little drop. And if it's just a little drop, does it really matter how much change? If we know that the number is going to be really, really close to 0.10? Yeah, no. So that's what neglecting the x is all about. We're going to try that out here. If it doesn't work, then we have to do the quadratic, but always try. So I'm going to say, okay, maybe this minus x can be neglected. And because of that, I'm just going to get rid of this in our bottom. And now we're going to try it out. We're going to find x, and then we're going to do a little test. So let's see. Now I'm just going back to math. 2.3 times 10 to the negative third times 0.1 equals x times x is x squared, right? So we got x squared equals, calculus out, 2.3. I just want to have the number in here, 2.3 times 10 to the negative third times 0.1. I get 2.3 times 10 to the negative fourth. If we want to get rid of the square, we have to do the square root. Boop. So square root of that. And in this case, it really doesn't matter for sig fig since we're, demonstrating. But I guess we'll take, 3 sig figs, because it's not really the answer yet, because we're not in the second ionization. So 0.152. Okay. Now, here comes the, we'll say, what's that word? I guess the check, right? It's called the 5% rule. And what you're going to do is you're always going to take the answer that you got, so 0.152, and divide it by the initial. Now, hold on a minute. Oh, sorry about that. I was going to say, how is that even higher? Let me just move this out. This is 0.0152. So let me just do that over again. So we're going to take 0.0152 and divide it by the initial, which was 0.1. And since it's a percent, right, 5%, we have to times by 100. If this answer is less than 5%, 5 or less, then we did a good thing. then we can say we can neglect the change. But if it's over 5%, we got to go back and include the negative x into our calculations. So let's keep our fingers crossed, but I don't think it's going to work, but we'll see. 15.2%, way over 5%, which means that the first ionization cannot be neglected. So let's just erase all this. So it did not pass the 5% rule, and we just have to go all the way back to this part and say, I cannot get rid of these minus x's. So I have to keep them there. Minus x, and now I put minus x in here. Now we do the math. So, I'm still going to times the Ka value by this, but now I'm going to distribute. Right now I have two terms down here. So it would be 2.3 times 10 to the negative third. Actually, we'll say this one is to the negative fourth. That's this times 0.1 minus 2.3 times 10 to the negative third x equals x squared. So here's the issue, guys. I have an x and I have an x squared. That's the quadratic equation. So whenever we have that, we have to pull over these two terms to the other side, right? Or you could pull the x over this way, but I think it's just easier if you have a positive x value for x squared. So what I'm going to do is, since this is negative 2.3 times 10 to the negative 3, I'm going to plus 2.3 times 10 to the negative 3x on both sides. And then, for this random number, it's a positive, so I have to subtract 2.3 times 10 to the negative fourth on both sides. Okay, so now this cancels. This cancels. This whole side is now equal to 0. And now if I just rearrange this, it would be x squared plus 2.3 times 10 to the negative third x minus 2.3 times 10 to the negative fourth. And there should be no x here. Sorry about that, guys. And this all equals 0. So now let me just erase this. Pause the video if you need this. But it's going bye-bye. Goodbye. And now we have to pull in our beautiful quadratic equation. Before we do that, though, let's just label our a, b's, and c's. Remember, the a value is in front of the x squared, but there's no number here, so that just means that it's 1. So a equals 1. The b value is the number that's in front of the x value. And you got to take into consideration that it's positive. So b would equal 2.3 times 10 to the negative third. And then the c value is the number all by itself. Take that value into consideration. It's a negative. So c equals a negative 2.3 times 10 to the negative fourth. Okay, now here comes the quadratic formula. Boop. We love it. So I'm just going to put it over here for reference, I guess. I think we could do it. Let's put it over here, right? So here's just negative b plus or minus the square root of b squared minus 4ac all over 2a. And we're trying to get that x value, right? So let's see. X equals a huge fraction, negative b, and the b value is 2.3 times 10 to the negative third. Close that up. That's a, yeah, I guess we don't need parentheses for that one because it's just negative b. So negative b, I'm just going to pull this over a little bit, plus or minus the square root of, now I'm going to put that b value in parentheses. So it was a positive 2.3 times 10 to the negative third. Close that up. That's being squared minus 4 times your a value, which is 1, times your C value, which is a negative 2.3 times 10 to the negative fourth. So I have to just pull this over a little bit. I think I have room. Let me pull this over. There we go. Okay. So negative 2.3 times 10 to the negative fourth. Close that off. Let's extend the fraction and the square root. And then it's all divided by 2 times a. A was 1, so there you go. I'm going to work off of this big fraction. We'll chip away at it one by one. The first thing you should do is obviously 2 times 1 is just 2. So just remove this, right? That makes it much easier. And now what you can do is you could plug this whole thing under the radical into the calculator as once, right? I'm going to do 2.3 times 10 to the negative third squared, and then I'm going to minus by 4 times 1 times negative 2.3 times 10 to the negative fourth. Let's see what we get. 2.3 times 10 to the negative third squared. 2.3 times 10 to the negative third squared. Okay. Then we have 4 times a negative 2.3 times 10 to the negative fourth. And then I'm going to take those two numbers and subtract them. Okay. And since this is not the final answer, I'm not going to round it. Well, we get 9.2529 times 10 to the negative fourth. Now do the square root of that. So we're just going to do the square root. And still I'm going to try not to round. It's a pretty long decimal, so maybe I'll cut it off after a couple of numbers. But it's 0.0304. We'll say 186. Okay. And this is all divided by 2. Let's move this out. Beautiful. Now, remember, when you're coming back to finding out what x is, right? These are your x values, and that's what x equals. You can never have a negative molarity at the end of the game. Now, this is where the thinking cap is coming on, even though we've been using our brains for the whole period, but let's just see, we got this. This way, there's 2 different choices we can make. We could either say negative 2.3 times 10 to the negative third plus this decimal, or we could say negative 2.3 times 10 to the negative third minus this. Now remember, we can only have a positive answer. So which one, positive or negative, are we going to add these two? Or am I going to take this negative and minus this? If I take this negative number and I subtract this, I'm going to become more negative. So the positive answer is the plus sign here. I don't care about the negative. So what I'm going to do is I'm just going to add these two and then divide by 2. So let's see, what do we get? Negative 2.3 times 10 to the negative third plus 0.0304. 186. I get that, and then I have to divide by 2. So maybe I'll cut it off after 2 sig figs now. 0.014. And that's molarity. Okay. Now remember, we still only care about the second ionization. So we just completed the first one. H2TE went down to HTE minus. So here are my x values, right? X and x. X was equal to 0.014 molarity. So I know that x, both of these, are 0. Maybe I'll just put them at the bottom. 0.014 molarity and 0.014 molarity. Okay. So now, let's pause the video if we need to. I'm just going to erase the quadratic equation for the first one because I have the x value. The only thing we needed was that the x value was 0.014 molarity. So goodbye to that. We're going to get rid of this math, but I'm going to leave the Ka value because we're going to do it a second time. Now let's just write the second equation, right? So let's see. The second ionization, which had a Ka value of 1.6 times 10 to the negative 11th, started with HETE. So the product that I formed now turns into the reactant. And now I'm going to treat this as an acid. So HTE minus will dissociate, right? Comes to equilibrium, it's a weak acid. One of the H's gets lost, so that just becomes H plus. And then, what do you have left over? Well, you just have TE, right? So plus TE 2 minus. Ice it out, right? Now, all of these are charges. So anytime that you see a charge, that's always aqueous. So these are all going to be included in my Ka equation. ICE. But now here's the thing. What's the initial HE? I knew I was going to make the mistake again. HTE minus, right? It can't be 0.1 molarity because that was H2TE. But, oh, that's what we found for the last question, right? Or the first ionization. Whatever you found for HTE minus at equilibrium, that's what you basically pull over. So the end for the last ionization is the start for the first one. That's why we had to do the whole thing. We had to get this number. And now let's see. Are we starting off with any H plus? Well, we ended with some H plus, so I have to start with some H plus in this example. 0.014. But now I have no TE2 minus. This is not TE2 minus, and these aren't TE2 minus. So I still say that I have 0 for that one, starting off. C stands for change, and since I have nothing for TE2 minus, I still know that my products has to increase. So plus for the H plus and plus for TE2 minus, which means that on the reactant side, we can subtract. Once again, it's a 1-to-1-to-1 ratio, so minus X, and plus X. Equilibrium, just pulling the initial and the change together. So it would be 0.014 minus X, 0.014 plus X, and X. Now, let's just rearrange this Ka equation because we just have different products and reactants. The H plus is going to stay there, but now HETE minus is going on the bottom because it's now a reactant, and then the TE2 minus goes up on the top. And since this is the second ionization, we're now going to use this Ka equation, or the number, right? So 1.6 times 10 to the negative 11th equals, let's see, I got 2 on the top, 1 on the bottom. Here we go again. If we add plus x's or minus x's into our equation, we're going to have to do the quadratic. So we always pretend maybe that ionization can be neglected, aka the change. So in this case, since this is a minus x, I can assume that, hey, maybe I just start with this, roughly, and this plus x, I can say, oh, maybe I just have 0.014 roughly around at the end of the day as well. I can't get rid of this x because then I won't have a variable. You always need to keep just the x's, but if it has like a plus in front of it at equilibrium or a minus, that's the ones that you get rid of. So it would be 0.014 times x divided by 0.014. Now let's see. Well, the top and the bottom are exactly the same numbers, so they can cancel out. And x literally would just equal this. Okay, so we tried to neglect it. Let's see if that's the case. We're going to do the 5% rule again. So we take the number that we just found as the x value, 1.6 times 10 to the negative 11th, and divide it by the initial concentration. In this case, it's 0.014. Times that by 100. Hopefully the answer is 5 or less. And if that's the case, we can neglect the ionization. So let's see, 1.6 times 10 to the negative 11th divided by 0.014 times 100. Whoa, this is a really small percentage. So this passes the 5% rule. This answer is like 1.14 times 10 to the negative 7th percent, way lower than 5. So that means that we can neglect the second ionization. So maybe I'll just write that. We can neglect the second ionization. It passes the 5% rule, which we just performed over here. But if that was the case, then you would have to go back and plug in your minus x's and plus x's and do the whole quadratic equation. But thank goodness we don't have to. We can neglect that second ionization, and that's it. So this question's done, and this section is done. So thank you for watching. I really hope that this is helping you out. We're moving on to buffers, which is so fun, and it's pretty easy, if I don't say so myself. I think it's pretty easy. It's mostly one formula, and you could do a lot with that formula. So just as long as you know that one formula, but we'll get into it, all right? So hang tight. We're getting into buffers. If you want to help us out, please press the subscribe button. Tell your friends, tell your classmates that this cool YouTube channel exists, and I hope you have a great day, all right? Okay, bye-bye.